All right. So it's my great honor to introduce our speaker today, Jiachao Liu. Jiachao got his bachelor degree from Peking University in 2009, majoring in geochemistry. And he got his PhD in University of Michigan in 2015, worked with Professor Jackie Lee, who is a GL alumni almost like 20 years ago. So then he worked with Jackie for another year to wrap up his paper before moving to Michigan State University in 2016 as a postdoc with Professor Suki Dorfman. So since last year in May, he started to work with my PhD supervisor, Arfu Ling, another GL alumni almost like 15 years ago. So Jiachao has been working on a wide range of scientific questions from methane hydrate at seafloor depths and mantle mineralogy and composition of the Earth's core. So for people who do carbon analysis, including myself, we have to buy Jiachao a drink because one of the carbon standards was synthesized by Jiachao. So let's welcome Jiachao and hear his talk on mantle redox.
So thank you for inviting me for the seminar. So today's talk is how does oxidized mantle differ from a normal mantle in geophysical and geochemical perspectives. So in this talk, I will show you both experimental and theoretical results on Fe3 plus only minerals and mineral assemblages. So comparing with previous Fe2 plus dominant systems, we can constrain how large the difference between an oxidizing mantle and a reducing mantle in both geophysical and geochemical properties. So as we know, redox state is a very important parameter in controlling the physics and chemistry in the interactions between different mantle reservoirs and also between the surface atmosphere and the Earth. Here, this is a cartoon shows an example how the mantle convection interact with the atmospheric oxygen level. So before about 2.7 billion years ago, the Earth's atmosphere is depleted in oxygen, and there is no global convection going on. And about 2.5 billion years ago, there was a significant increase in the oxygen level, which is named as a Great Oxygen Event. And during the same time, there is an initiation of subductions, which could transport reducing materials such as oxygen sinks, like reducing iron, to the deep mantle. So the atmospheric oxygen can be accumulated. And also, in addition, the deep mantle degassing can also influence the oxygen level in the atmosphere through volcanisms. So here is those two figures show the comparison between the redox conditions of the mantle and the corresponding Fe3 plus content. And from the surface to the core mantle boundary, the mantle becomes more and more reducing because at the surface we have free oxygen, but at the core mantle boundary, the mantle directly contact with metallic liquid, which ensures very reducing environment. But intuitively, we would expect at more reducing environment, iron should be in like either Fe2 plus or metallic iron format. However, there are more and more evidences showing the lower mantle could have more Fe3 plus compared with the upper mantle, although it's more reducing. Here is a Pyrolitic model of the Earth, which shows with depths what are the major minerals and what are their proportions. And in the lower mantle, the major mineral is bridgmanite, and also the deep mantle garnet majorite. Both of them can incorporate significant amount of Fe3 plus. So that's why the lower mantle can be enriched in Fe3 plus. So the first evidence supporting this argument is from high pressure experiments, where people find when bridgmanite and garnet coexist with metallic iron, their Fe3 plus can be still very high. In contrast, the transition zone minerals, ringwoodite and wollastonite, both can only incorporate limited amount of Fe3 plus. And another line of evidence coming from first principle calculations. So in order to match the density and the sound velocity profiles of the prime, Wang et al. Conclude the Fe3 plus content in bridgmanite can be as high as almost 100%. So that means the bridgmanite in the lower mantle really have the capability to incorporate a lot of Fe3 plus. So the third evidence is coming from natural sample. Here is a recent paper found a natural garnet coming from at least 380 kilometer steps. And its iron content to total iron, the ratio is super high, it's to the 97%. So although there are more and more evidences showing, we have a Fe3 plus rich lower mantle, but there are still some open questions regarding Fe3 plus in the lower mantle. For example, this cartoon shows some recent papers come up with the idea when sedimentary girsite or hematite being transported to the lower mantle, it could form a new iron oxide phase called iron peroxide. And through this phase transition, it can decouple the hydrogen and oxygen cycles in the deep mantle. And also this component could be an important component in the deep mantle seismic anomalies, for example, the ultra-low velocity zones sitting on top of the core mantle boundary. However, it's still not clear when you look at the experimental results, it's not clear how does either hematite or girsite react with the surrounding mantle. Would they react with the surrounding silicates before they are reaching to the desired PT conditions? And also this cartoon illustrates a very important phenomenon about the slab stagnation, which has been observed in many locations globally. And we would wonder, how does the trivalent cations Fe3 plus influence the morphology of slabs? Will the presence of Fe3 plus facilitate slab subduction, or it impede slab subduction? So another question regarding Fe3 plus is what is the spin transition pressure temperatures for the lower mantle bridgmanite, and how that influence the geophysical properties as density, sound velocity, electrical conductivity. As bridgmanite is the most abundant mineral in the lower mantle, it has two cation sites, and both the pseudo-dodecahedral site and the octahedral site. And both sites can incorporate Fe3 plus, but based on recent theoretical and experimental results, people reached the agreement that only the B site Fe3 plus can experience a spin transition at the lower mantle pressure temperature conditions. But it's still unclear where does that happen and how the spin transition influence the bridgmanite's thermoelastic properties and electric and magnetic properties. So we need to keep in mind that the lower mantle is pretty homogeneous in terms of the 1D seismic profile and density profile and the electrical conductivity. So if we observe any anomalies caused by valence state or spin state in bridgmanite, we need to think about how to reconcile the mineral physics observations with the geophysics observations. And the third question is for the mid-ocean basalt, they exhibit heavy iron isotopic compositions than chondrites or other planetary bodies. And one theory or one mechanism is a recent paper showing the valence state could play a role in iron isotopic fractionation. So this figure shows the relation between Fe3 plus content and its corresponding iron delta 56 composition. And it shows a positive relation, which means if the melt is more oxidizing, it can concentrate heavier iron isotopes. And back to the lower mantle, since it's very likely the lower mantle bridgmanite can be very enriched in Fe3+, but the other major lower mantle mineral, ferropericles, can almost only take Fe2+. So we would wonder how does iron isotopic fractionate among those two lower mantle minerals? Especially in both minerals, spin transition can also happen. So we would want to understand how does the valence state and the spin state influence iron isotopic distribution in the lower mantle. So here are those three questions I try to answer in this talk. The first one is, how does hematite react with mantle silicates along subductions? And how do the trivalent cations influence the slab morphology? The second question is, in the lower mantle, how does the valence state and spin state of iron influence the density, sound velocity, and the electrical conductivity properties? And the third question is, how does iron isotopic fractionate between bridgmanite and ferropericles in the lower mantle pressure temperature conditions? So as an experimentalist, I use both Martin Anvil and Damon cell to conduct experiments to understand those questions. So the Martin Anvil apparatus I use is from University of Michigan, Professor Jackie Lee's lab. And as people who are not familiar with this, we load a sample in millimeter scale to a sample capsule. Then it is surrounded by a ceramic octahedra. And this octahedra is comprised by 8 tungsten carbide cubes. And the outer stage are 6 stainless steel anvils. So we put everything here to this ring and apply oil pressure and to the target pressure. Then we do resistive heating and hold for long enough time to study the phase relations for my purpose. And the advantage for this technique is we can really well understand the compositions and chemistry in the run product, because this is large enough for electron probe analysis. However, it has limited pressure temperature ranges. For our facility, it can only reach to the uppermost lower mantle PT conditions. So as a complementary technique, we also use this Damon cell device, which has the capability to cover the whole mantle pressure temperature conditions when it coupled with laser heating system. And we also use a variety of synchrotron-based techniques to probe the physical and chemical properties of our sample under the relevant pressure temperature conditions. And we also use a variety of analytical measures, for example, the electron microprobe to study the compositions of our run products, and several synchrotron techniques like X-ray diffraction to understand the structure of our sample and monitor the structure, phase transition, and also spin transition with this technique. And we use Mossbauer spectroscopy to determine the Fe3+ to total iron ratio in our sample, and use X-ray emission to monitor the spin transition under pressures, and use this nuclear resonant inelastic X-ray scattering technique to study iron isotopic fractionation. And we also collaborate with 2 groups who do first principle calculations. One is from USTC, the other one is from UNLV, to cross-validate our experiment data and theoretical results. And what extra information they can provide is what is the physics behind our experimental observations in not only atomic scale, but also in electronic scale. So back to the first question, what will happen when sedimentary Fe2O3 being subducted down to the uppermost lower mantle pressures? So what we do is we run Martin-Anvil experiments by using a mixture of MgSl3 together with 10 molar percent Fe2O3 and cook them under the target pressures and temperatures for long enough time to reach equilibrium. And before we are looking at the results, here are those two phase diagrams for those two end members. And actually, for the most part of the lower mantle, those two end members adopt the same structure, perovskite structure. That would indicate they can form solid solution very easily. However, at the upper mantle pressures, those two have very different structures. One is for MgSl3, it is either clinopyroxene or other pyroxene, which both of them are very different from ilmenite structure. But for the MgSl3, it adopts the ilmenite structure in the transition zone pressures. So here is one example about the experiment we run by using this starting material at 24 GPa and along a geothermal. Supposedly, before we open the sample up, we would expect this would form a single phase where both magnesium side and silicon side are occupied by 10 molar percent iron. But very surprisingly, we are seeing two phases. And for the dark phase, it is a normal bridgmanite composition. And based on Raman measurement, it is bridgmanite. And what is so surprising here is we are seeing a bright phase. And this bright phase, if you look at it, it has a 1-to-1 ratio between those two end members. And this composition hasn't been observed in previous Martin-Envol experiments at all. So we want to understand whether this phase will occur in different other pressures. So we run another experiment at 10 GPa where MgSl3 is in clinopyroxene stability field. And in this case, we also see two phases. But the bright phase is pure hematite. So no magnesium or silicon enter this bright phase anymore. And so there's basically no reaction between those two starting materials. So how about the other pressures? So we run other experiments at the stability field for ilmenite or wollastonite. And as long as the pressure is beyond the clinopyroxene, we always see this bright phase with a composition similar like 1-to-1 ratio between MgSl3 and hematite. And together with a dark phase, which is a normal mantle composition, either bridgmanite, achimotite, or wollastonite. So from those experiments, we conclude here is when hematite or Fe2O3 being transported down, when the slab reaching to the transition zone, this phase will be eaten up by the surrounding silicates and form this 1-to-1 ratios. This is a small amount based on mass balance, but this is the major Fe3 plus carrier for the sedimentary hematite. So, but what is the structure of this phase? What is the structure of this phase? Yes. So we conduct synchrotron X-ray diffraction measurements by loading this single phase to the diamond cell and compress it without any heating. And it turns out this phase below 20 GPa, it adopts achimotite structure. And it changed to pure bridgmanite around 25 GPa. But what is so special here is we didn't apply heating at all. So for people who synthesize bridgmanite, we know we always need some kind of heating, either resistive heating or laser heating, to overcome the kinetic barrier to facilitate the phase transition. But this is the first time we are seeing for silicon and magnesium bearing perovskite, no heating is needed to synthesize pure bridgmanite. So in order to understand the physics behind, we collaborate with people who do first principle calculations. So what Dr. Zhu does is to see how much energy cost through achimotite structure to bridgmanite structure and pass through a transition state. So he calculated both our composition and also pure MgSl3 composition. And what you can see is for the pure magnesium end member, it really costs a lot of energy. So that's why when you synthesize iron-free bridgmanite or bridgmanite with a little bit of iron, you always need heating. But for our composition, it doesn't require, the energy is so low, so you don't need to really heat that. sample. And by the way, for hematite or Fe2O3, you can also cold synthesize bridgmanite without any heating. And more intuitively, when we look at the structure between perovskite, archimontoite, and the lithium niobate, which is the structure as Fe2O3 in the hematite structure. So those two are very similar in terms of the structure. So from lithium niobate to perovskite transition, you don't need to break any chemical bond. Instead, you only need to tilt the octahedral a little bit and push the large cation to one side. Then the phase transition happens. So that's why you don't need to heat. But for archimontoite, it has two different octahedral size. And when you reconfigure it to perovskite structure, you need to break bonds. So that's how you need to always heat the sample. And for our composition, because it looks like a one-to-one mixture between MgSl3 and the hematite, and in terms of this phase transition, it behaves more similar as Fe2O3. So is there any geophysical applications for such a low energy cost phase transitions? So here is a figure shows the density anomalies in a slabs when it penetrates a transition zone. Because in the transition zone depths, there are several phase transitions. And at the bottom of the transition zone, both post-spinel and post-ilmenite structure transitions, they have negative Clapeyron slopes. So which means for the cold slabs, those phase transitions got delayed, and which can make the slabs lighter at those depths than the ambient mantle, and then this mechanism have been proposed for the slab stagnation. However, if as the previous slides show, if the slabs is enriched in trivalent catons, it's not necessarily Fe3+, it can be aluminum also. So this phase transition can be facilitated, this post-ilmenite transition. So it's no longer, it has almost a zero Clapeyron slope. So we would expect for such a slabs, the kinetic barrier is not an issue anymore. And then we calculate how much archimontoite for a Hasbergite composition along different geotherms, and to see whether this phase transition, this post-ilmenite phase transition can be significant enough. And it turns out for cold slabs, archimontoite can be the dominant phase at the bottom of the transition zone pressures, which can occupy as much as 80% in like mass. So in this case, we calculate the corresponding density profiles of those three geotherms and also plot the prime. And for the cold slab, because it has significant amount of archimontoite, so the phase transition from archimontoite to perovskite can cause as high as 4.7% density jump. And so it makes the cold slab density is higher than the ambient mantle. So we think the conclusion here is for Fe3+ rich or aluminum rich slabs, the kinetic barrier is not an issue for slab to penetrate into the lower mantle. And so the next question is, what happens for Fe3+ in the lower mantle? Since the bridgmanite is a major Fe3+ carrier in the lower mantle, so in the rest of this presentation, I will focus on bridgmanite specifically. And so far, like people reach agreement that only Fe3+ in the small octahedral side would experience spin transition. But where did that happen? And how did that influence the geophysical properties? People still not reach agreement yet. So since 2004, people report the spin transition in perovskite or bridgmanite. They draw different conclusions, although for people who work on similar compositions, the conclusions can be very different. For example, some people think, oh, for this composition, there is no direct spin transition happens. And there would happen, the spin transition would happen around 60 GPa or 120 GPa. And how about the influence? Will there be a gradual change or will be a sharp change, which could be more interesting since it can also cause a observable abnormal in the seismic data or other geophysical observations. But people draw different conclusions about whether it's gradual change or sharp change. So this one I want to give you the impression that it's still not clear yet. So our Bridgmanite sample actually is a very ideal sample to clarify this problem, because for the first reason is we only have Fe3+. So we don't have any interference from Fe2+. So any anomalies observed in this sample should be attributed to Fe3+. Secondly, as we see before, the synthesis from achimotoite to perovskite or Bridgmanite doesn't require heat. So heating can always cause some problems like the chemical diffusion, Sorry diffusion, and the valence redox reactions. So, but in our sample, we don't engage any heating, so to make the data as clean as possible. And thirdly, we have about 10 times iron content than the normal Bridgmanite composition. So any influence of the spin state could be more clear. It's beyond the experimental uncertainties. So here is the compression curve of our sample, which we show a clear softening around 50 GPa. And we also see that in this corresponding stress strain diagrams. It's a huge change in the slope. So this softening is always related to spin transition. But from the equation of state data, we don't know how much of the iron experience spin transition. Will all of them or just half of them? So we further conduct X-ray emission measurements on this sample. And what we see is those are the X-ray emission data. And for this satellite peak, its area is associated with the spin moment. And what we see is it starts to drop around 30 or 40 GPa and reach plateau to about 60 GPa. And then we can derive the corresponding spin moment for the initial and which is the black squares. And the initial value is 2.5, which corresponding to both A side and B side are high spin state. And finally, it reaches a plateau around 1.5, which corresponds to only one side spin transition only occurs in one side, and the other side is still high spin state. And in this case, we are seeing only half of them lost the spin moment. And based on the theoretical calculations, the A side or pseudo-dodecahedral side is too large for Fe3+ to have spin transition in the mantle pressure ranges. So we confirm previous results that only in the mantle pressure temperature conditions, only the B side Fe3+ can have spin transition. And how about its consequence, like in geophysical properties? So here is a figure showing a comparison between Fe2+ Bridgmanite as those black lines, together with either high spin Fe3+ as those red dashed lines, or or low spin B side Fe3+ as those solid lines. So what we are seeing is for most properties, the Fe3+ Bridgmanite and Fe2+ Bridgmanite, they separate well for the very iron-rich end members. So our samples serve as the pure iron end members here. However, for the normal mantle compositions, which has about 10 molar% iron, the separation is within experimental uncertainties. So that means neither spin state or redox state could be distinguished for a normal iron content in the mantle. And also, since the spin transition happens in our sample, we are wondering what is the influence in electrical conductivity, especially the previous results on the Bridgmanite electroconductivity are still very controversial. For example, Ota et al., they find a significant drop of the electroconductivity for this Bridgmanite sample and attributed this drop starting at 70 GPa to spin transition. And a more recent paper, Simio et al., found that there is no observable dip at all. So it's a smooth increase. So in order to clarify how does spin transition influence electrical conductivity, we also use the four-wire methods to measure the electroconductivity of our sample. We did two sets of experiments, and the results are pretty reproducible. And what we found is within the pressure range of the spin transition constrained by X-ray diffraction and X-ray emission, we are seeing a small dip, which is only 0.3 log unit. And considering our sample has 10 times iron content than the normal mantle, and also temperature would broaden this influence, we would expect no observable influence of spin transition on the mantle electrical conductivity. So here is back to the geophysical observations, which shows pretty smooth profiles in density, sound velocity, and the electrical conductivities. So our observations actually reconcile the mineral physics results and the geophysical results. So back to the last question. So how does iron isotope fractionate in the lower mantle? So here is an indicator that the valence state of iron could play a role in the isotopic fractionation. And so in order to address this question, we conduct nuclear resonant X-ray scattering measurements on this sample where the income X-ray excite the iron 57, which is the only sensitive isotope to this technique. And in the meanwhile, it involves phonon accretion and annihilation. So from those inelastic peaks, we can tell the vibrational properties of this sample. And what the data processing is, we analyze the third moment of those inelastic peaks to derive the force constant. And this force constant, you can treat it as a bulk modulus of iron sublattice, so which tell us how strong is the iron bonds. And from this force constant of different phases, we can calculate the delta iron 56 and with the dependence of temperature. And this is our experimental results from around 33 GPa to 100 GPa, and which stand for, based on our X-ray emission, X-ray diffraction data, they stand for the A side high spin, B side high spin. But this one has A side high spin, B side low spin. And what you can see is they have a observable shift to higher energy. This is the partial density of state for iron in those two samples. And what you can see is a shift to higher energy, which indicate an increase in the force constant. But by using this technique, we probe an averaged force constant of both sides. So in order to see how large change in the force constant from the B side spin transition, we collaborate with Dr. Wu and graduate student Wang from USTC to calculate the phonon density of state in our sample. And those red curves are their calculation results, which match really well with our experimental observations. And what is really cool is they can tell what is the A side Fe3+ and B side Fe3+ look like. And when both sides are in high spin state, they are not differ a lot. Both are centered at the same locations. But once spin transition happens, it really shifts the p dots of B side Fe3+ significantly. And such a shift corresponds to a significant rise in force constant, which means it can concentrate heavy iron isotopes. So here is the derived force constant from the NRIX data. The red squares are our experiment data for this Bridgmanite composition. And what we see is this is the average force constant between A site and B site. And we are seeing about 30% jump in force constant. And compare with literature data on bridgmanite, actually below the spin transition, they really look very similar, especially when you consider the large uncertainty in NRIX is about 10%. And also, we, in Professor Afulin's group, we conduct the measurements for ferropericles also. And again, before the spin transition, everything looks very similar, which implies, like in the shallow part of the lower mantle, there are not much isotopic fractionation. But above the spin transition, first of all, ferropericles exhibit the highest force constant among those minerals. So that is because iron in ferropericles all experience spin transition. But in our sample, only half of them experience spin transition. So it only rises to half a way. But also, the B side Fe3 plus spin transition distinguish this sample from other bridgmanite. So then we calculate what are the isotopic fractionation like at different depths. At 40 GPa, where no spin transition happens, everything looks very similar. So the fractionation is really small between ferropericles and bridgmanite. So this purple bar marks the isotopic composition for MORP. And back to the deep mantle, where spin transition already occurred, they really separate with each other. So when the red curve is a calculated isotopic fractionation between ferropericles and Fe3 plus bridgmanite along different temperatures, which cover the whole temperature range at these depths. And very interestingly, this magnitude could match this purple one. But the fractionation can be even larger between ferropericles and Fe2 plus domain bridgmanite. It can be as high as 0.3 per mil. So here are the conclusions I ended up. So based on our multi-level experiments, we conclude Fe2-3 is not a single phase, like when slabs penetrated the transition zone. In fact, this solid solution forms, and it could become the major Fe3 plus carrier in the deep mantle. And so the enrichment of either Fe3 plus or aluminum could facilitate this post-Akimotoite phase transitions, and it would make the kinetic barrier is not an issue anymore. And based on our synchrotron measurements on this Fe3 plus only bridgmanite, we conclude neither oxidation state or spin state is important to cause observable geophysical anomalies. And the last conclusion is due to the spin transition, heavy iron isotope should concentrate in the lower mantle ferropericles. And I would like to thank my collaborators. So most of this work was done when I was a postdoc working with Professor Susanna Dorfman in Michigan State University. And we got support from my PhD advisor, Jackie Lee's group, and also I'm currently working with Professor Afulin on the same topic. And we collaborated with many scientists working in Argonne National Lab, including people from University of Chicago, and from HBCAD, and from University of Hawaii and Argonne National Lab. And we collaborate with our collaborators for doing theoretical calculations are from USTC and UNLV. So I will stop here and happy to take questions.
Questions?
Back. Yeah.
So yeah, this is a very interesting finding, this phase. My question is this is intermediate compound or you're finding as a solid solutions? So have you done a series of experiment with different hematite star material. Is saturated and is from your experiment it wasn't clear. Are you getting a variable?
Yeah, this is a PDF version actually. Like for people who study MgSl3 to aluminum, like this system, people find they have the phase diagrams look like it disproportionate to a magnesium-rich member and aluminum-rich member. And from Geo, I know you guys calibrated the metal using this, the solubility of aluminum in this phase. And I think this is kind of similar to that phase diagram, which is, I think this is a end members, but we didn't change the starting materials or the proportions, but we changed the pressures, which always show two components. One is magnesium-rich member, one is this compound with some like very small variations. So it looks like this is an end member. Instead of this Fe2O3 is an end member, this component can serve as an end member in the phase diagrams. But it's very interesting to study, to explore the whole phase diagram, what that look like in future.
I had a question about the the theoretical calculations of high spin and low spin.
Oh.
Did they send you equation of state
Yes,
data also? And did
yes,
they match?
they do give us the equation of state. Let me see if this probably don't show all the hidden slides. Let me work. Yes, they did calculate the equation of state to match our, like the match is really good. I can show you the results. So this is the results from the theoretical calculation. They calculate for this composition what is the equation of state look like. And this is the blue curve is the low spin state, and they really match well with ours. Great. And as you know, they do the GGA plus U, so it's always some little offside, but it's acceptable. Great. And back to phase question. So this is what I would expect the phase diagram look like, but I'm not 100% sure yet. So what that means, this is a MgSl3 to this end member, and what we saw is with pressures, we always see this phase, so that make us to draw the conclusion. This serves as an end member, but not an intermediate component. So that's what we saw so far.
Can I ask another question? I have another question about the electrical conductivity.
Yeah.
You showed like a pretty dramatic increase with pressure in your data, but then you said that it matched geophysical observations. I know you're talking about the lack of a signature of spin transition.
Yes.
But does the trend over from the top of the lower mantle to the bottom, does that reconcile with geophysical observations?
That's a really good question. The answer is I'm not sure, because first of all, our composition has unrealistic high iron content, and although you look like the Siemens paper, the slope are not differ a lot, and but here the uncertainties, but I'm not really know how large the uncertainties in those geophysical observations, but it looks like it's order of 10, like within uncertainties. So I'm not sure whether in terms of the slope, whether they can also reconcile with each other. So it's a very interesting question. Yeah.
Comments. I mean, it's understandable. You're looking at the subduction zone and as a carrier to the ferric ion, but now you're talking about the global mantle here, and so maybe it's not really that conclusive in terms of apply to a 1D global mantle composition, because this is probably more localized phenomenon.
Oh, the reason we draw that conclusion is our samples serve as an end member. We are not saying this component itself, but we do an extrapolation to the pure magnesium end member. So we presume that is a linear relation. And our data are plotted here. So we are talking about for the normal mantle compositions, we want to see how large the difference between different spin state and oxidation state. And it turns out all the experimental data mixed, like overlap with each other. So we draw that conclusion. This is probably not visible.
But there's the reason, that's why actually it's important to look at as a low ferric ion, low hematite concentration, because that defines the bulk compositions. So what I suspect is because you start with such high ferric ion content, you separate those two phases. But if you look at the low, there must be a limited salt solutions for the ferric ion in bridgmanite,
right?
Which we know from some of the synthesis we have done.
Right.
So question is, how far is that the maximum ferric ion solubility in the bridgmanite, which will define the bulk composition? Then you can actually talk about the whole mantle compositions.
Right. You're talking about this part, the solubility in this part. Yes. Yes.
Falling in that particular space, then you really can't use that as an end member to discuss the whole mantle.
Yes.
Any more questions?
I'll ask just a simple question if no one else has any. So you get in elastic scattering, you get a partial density of states of iron.
Yes.
What do you mean by a singular force constant? How do you obtain that from those data?
So from here, you're asking about the data processing procedures. So what we do is, yes, they take the third moment of the inlet scattering and do the integration to get the force constant.
So I have a question. So how did you characterize the Fe3 plus in A site and B site in your sample?
In my sample, it is, first of all, my sample is simple because when we do the chemical analysis, it's basically, it only has like a 0.5 magnesium, 0.5 silicon, and then the leftover iron. From the stoichiometry, we can assign that. And another thing is we did the Mossbauer measurements, and it turns out all the iron are Fe3 plus based on the small quadruple splitting, and so we think that is based on the formula and also Mossbauer, we think all iron should be Fe3 plus, and then when the charge balance, we think half of them distribute in the A side, half of them distribute in the B side.
Do you have ambient data?
The ambient Mossbauer data, yes, I didn't plot here. Yeah, we do have ambient data. It shows like only 1 bit in the synchrotron Mossbauer, so very small cut of split.
There's a fractionation at 100 GPa between bridgmanite and ferropericlase. That's a much different thing than saying that that's the reason for the enriched morb at the surface, right?
Yes.
Okay.
Yes. So we are still working on how do those signatures are being transported down up to the shallow depths. It's still ongoing. So we are not talking about anything about morb like from our results.
That then brings up the issue of the observation is that the oxidation state of the mantle hasn't changed throughout Earth history. So you can't really be subducting lots of ferric iron.
Yes. We would expect that occurs during the great oxygen event where the banded iron formation has a peak occurrence. And that part is probably where much Fe super has been subducted to the lower mantle. So it's not a present process.
More questions? All right, let's thank our speaker again. So if you want to chat with our speaker, please join us for lunch.